Hey everyone, and welcome to Electro Knowledge. Today we are going to tackle a super important topic in any electrical system, power factor correction. We're going to break down how you can turn hidden electrical waste into some serious efficiency. But first, let me ask you a quick question. Are you literally paying for electricity that does absolutely no useful work for you? Because if your facility has a low power factor, well, that's exactly what's happening. And it's probably costing you a whole lot of money.
Electro Knowledge. Power up your concepts.
So here's our game plan for this explainer. We'll start with what power factor even is. Then we'll dig into the problems a low one can cause. After that, we'll cover the fix, see how it works in the real world, check out all the benefits, and then wrap it all up with the key takeaways. Let's jump in. All right, first things first. What exactly is power factor? Before we can fix the problem, we've got to have a really solid grip on the basics of power in AC circuits. To put it simply, power factor is just a number, somewhere between 0 and 1, that basically gives your system an efficiency score. If you've got a perfect score, a power factor of 1, that means every single drop of power you're pulling from the grid is doing actual useful work. Anything less than 1, well, that means there's waste in the system. To really get this, you need to know about two different types of power. First up is real power, measured in kilowatts. This is the good stuff, the working power that actually lights up a room or spins a motor. But then you've also got reactive power, measured in kVAR. Think of this as magnetizing power. It doesn't do any useful work itself, but it's absolutely essential for creating the magnetic fields that things like motors and transformers need to run. And there's a fantastic analogy for this. Think about a glass of beer. The liquid part, the beer itself, that's your real power. It's what you actually paid for. The foam on top, that's the reactive power. Now, you need a little foam for a good beer, right? Just like you need some reactive power. But if you get a glass that's half foam, you're paying for a full pint but not getting it. That's a low power factor. And this right here, the power triangle, this is where it all comes together visually. You've got real power on one side and reactive power on the other. The combination of the two, the hypotenuse of the triangle, is called apparent power. That's the total power your utility has to generate and send to you. So if that reactive power side gets too long, your apparent power gets much, much bigger than the real power you're actually using. Okay, so that brings us to the heart of the matter, the big problem with a low power factor, which comes with all sorts of hidden and not so hidden costs. So what are the usual suspects here? Well, the number one cause is something called inductive loads, and these things are everywhere, especially in commercial or industrial settings. We're talking about motors, transformers, pumps, fans, even older types of lighting. All of this equipment needs that reactive power to build magnetic fields, and that naturally drags the power factor down. So what's actually happening on an electrical level? Well, you can see it right here. In a circuit with these inductive loads, the current waveform gets out of sync with the voltage waveform. It starts to lag behind. This desynchronization, this phase shift, is the root cause of the inefficiency. The bigger the lag, the worse your power factor gets. And the consequences of this are pretty serious. A low power factor forces your whole system to draw more current to do the exact same amount of useful work. That extra current leads to more energy just being wasted as heat in your wires and transformers. And it can even cause voltage to drop, which isn't good for your equipment. But you know what the most painful part is? The one that hits your wallet? It's your electricity bill. Utility companies actually penalize customers with low power factor because it puts extra strain on their grid. Just to give you some perspective, a typical facility with a power factor of just 0.82 could be slapped with over $50,000 a year in penalties alone. That's money just gone. Okay, that all sounds pretty bad, right? But the good news is there's a very straightforward and effective fix. So let's talk about power factor correction and how you can start reclaiming all that wasted energy and money. The basic idea here is brilliant in its simplicity. We know the problem is lagging reactive power, which comes from inductive loads like motors. So the solution is to introduce its electrical opposite, leading reactive power, which comes from capacitive loads. It's like a perfect counterbalance. They effectively cancel each other out. So here's the play-by-play. Your motors are sitting there gobbling up all this lagging reactive power. So what you do is you install a capacitor bank right there, near the motors. These capacitors then start supplying the exact opposite kind of reactive power, leading reactive power, right where it's needed. Because it's being generated locally, it doesn't have to be pulled all the way from the utility. From the grid's perspective, the two just cancel out, and boom, your power factor shoots right up. Okay, so theory is great, but let's get real. What does this transformation actually look like when you put it into practice? And this diagram, wow, this says it all, doesn't it? Look at the top system. Without PFC, it has to draw this huge amount of apparent power from the utility. It's inefficient, it's costly. Now look at the bottom. Once that PFC unit is installed, it handles the reactive power on site. The result? The total power drawn from the grid shrinks dramatically, the system runs more efficiently, and the bills start going down. Let's crunch some quick numbers to see the impact. Imagine you've got a 100 kilowatt load, but your power factor is a pretty bad 0.70. To power that load, you'd need to pull almost 143 kVA of apparent power from the grid. Now let's install a PFC unit and get that power factor up to a healthy 0.95. That same 100 kilowatt load now only needs about 105 kVA. That is a 26% drop in the total power demand on the grid, and you didn't even have to change your operations. So where do you see this stuff in action? Well, pretty much anywhere that uses a serious amount of electricity. We're talking industrial plants, huge commercial buildings, data centers, electrical substations, and even renewable energy sources like wind farms. They all rely on power factor correction to run efficiently. All right, so what's the grand total of all these benefits? What's the real payoff here? Because it goes way beyond just saving a few bucks on your utility bill. Now, this is a benefit that a lot of people miss, but it is huge: the impact on how long your equipment actually lasts. By lowering the total current flowing through your system, PFC reduces all that heat and stress on your components. I mean, look at these numbers. You could see the lifespan of your transformers go up by 20 to 30%. Your cables could last up to 50% longer, and you could double the time between maintenance for your switchgear. That is a massive long-term win. This chart here breaks down the whole picture perfectly. Yeah, the biggest piece of the pie is getting rid of those nasty utility penalties. But right behind that is reducing your demand charges. Plus, you actually increase your system's capacity without needing to install bigger wires or transformers. And of course, you make your equipment last longer and even shrink your carbon footprint. It's a win-win-win-win. Okay, let's bring it all home and turn all this theory into a few simple, actionable takeaways that you can remember. So if you're going to remember anything from today, let it be this checklist. Number 1, a low power factor is just wasted money, period. 2, the main cause is inductive loads, like motors. 3, the solution is capacitor banks. 4, the benefits are huge: lower bills, more capacity, and longer lasting gear. And finally, the magic number you should be aiming for is a power factor of 0.95 or higher. So, I'll leave you with this question to chew on. Now that you know how much this kind of inefficiency can really cost, what hidden electrical waste might be lurking in your own system? Hey, if you want to master more electrical engineering concepts just like this one, and you want it explained in the simplest, clearest way possible, make sure you hit that subscribe button for Electro Knowledge. Thanks so much for watching.
Thanks for watching. Like, share, and subscribe to Electro Knowledge for more electrical concepts.